Welcome back to Physics 142. In this video, I'm going to do another example of calculating the magnetic field at some spot P using the Biot-Savart law. And for this example, I want to think about a straight wire. Right? We're going to have a straight wire that it has length 2a. So we'll have the wire go from minus a to a. And I want to think about what's the magnetic field at some point P that's a distance r, big R, away from the center of this wire. All right, I want to think what's the magnetic field at this point P, all right, a distance r away from this wire. So find the magnetic field at spot P. So to do that, we're going to have to think about all of the little pieces of wire, right, all the little pieces of this wire, and how all of the little pieces of this wire contribute some magnetic field to this spot P. And the formula that we use to do that is the Biot-Savart law. So let's write down Biot-Savart. So Biot-Savart says that B is equal to the integral over our whole wire here, right? The integral of our wire of mu naught times I over 4 pi times dl cross r hat, right? Both of those being vectors, divided by little r squared, the distance from our little piece of current to the spot P. So let's dive right into it. So let's think about a little piece. We're going to need some example little pieces of this wire, right? So there's an example little piece here, right? Or we'll maybe a little piece here, a little piece here, right? We chop this wire into a bunch of little pieces. So this is my piece IDL, right? It's my little piece of wire here. And IDL is a distance little r away from the spot P, right? And each different little IDL will be a different little r away from spot P, right? And if I want to think about, okay, what's the magnetic field from this IDL? Well, I can use the Biot-Savart formula. So let's see what we have. Mu naught, that's a constant, that comes out. 4 pi, those are both constants. And all along the wire, the I is going to be the same all along the wire. So I'm going to go ahead and pull that out of the integral as well. All right. Now inside the integral, I have to deal with this cross product. That's the first thing I have to deal with, right? So let's think about what the cross product is between dl and r, not our vector, our hat. There we go, our hat, right? So our hat is just the direction from IDL to P, right? So this would be the r hat vector, right? Would be that vector in that direction towards P. And so IDL, well, that's, we'll have the current flowing up in this wire. So IDL will be this direction here. So that's the direction of IDL. And so if we take this cross product, well, the cross product says we need the magnitude of dl times the magnitude of r hat, and the magnitude of r hat, it's a unit vector, so that's just 1, times the sine of the angle between them, right? Times the sine of the angle between them. And what's the angle between these two vectors here? Well, the angle between these two vectors, that's this angle here, so we can label that as angle phi here, right? That's the angle between those two vectors. And then we still have the r squared on the bottom. Now to actually compute this integral, right, to make, well, okay, first of all, actually, we're not quite done. So what is the actual direction here? Well, if we think about that cross product, I got IDL, that's going up. R hat is pointed that way, right? My fingers, there we go that way. And so my thumb is now pointed into the board. So the resulting direction here is into the page or into the board, all right? And we could double check, but that's going to be the same all along this wire, all right? All of these cross products are, no matter how I orient it, my thumb's always going to be into the board along the whole wire. And so that's good. That means that they'll just add up nicely as we go along the wire. Everything's the same direction, all right? But our resulting magnetic field is going to be into the page because each of these is going to contribute a vector that's going into the page. All right. I think in my coordinate system, into the page would be the minus z hat direction if I had an x, y, and z direction, right? But into the page, that's the direction here. All right, so we've handled the cross product, all right? But to make any progress, we have to now replace dl, sine phi, and r in terms of variables that we can actually integrate, all right? And the relevant variable to integrate, right, as we think about, we want to think about where are we in space, right? That's the variable we want to integrate, is going to be along y here. So it would be really nice to have all of these things in terms of where we are, right? In terms of our different position along the wire. And our position along the wire, well, we're going to represent that with the variable y. So let's work on that. All right, so we have mu naught times I over 4 pi. And now we're going to integrate, and we're going to integrate in terms of y. All right, we want to integrate all of these different positions y. And so we'll start at y equals minus a, and we'll end at y equals a. All right, so those will be our limits of integration. Now we need to replace these things. So dl, how is dl related to dy? Well, dl is just a little bit of space in the y direction, right? It's just a little chunk in the y direction. So dl actually is just, we could just replace that directly with dy because it's in the y direction nicely, all right? So dl, let's just go ahead and replace that with a dy, all right? Now, what about little r? All right, what is little r? How can we relate that to y and the variables that we know in the problem? Well, little r here, that's part of a triangle, right? Here we have a right triangle with little r, big R, this distance, and our position, right? Where our position is along the triangle, right? So little r is going to be the square root of big R squared plus our location along here. And if we start down here, we're at minus a, right? But if we're just part way down, we're maybe at some position minus y, right? Down here we're at, maybe a third of an a or something like that, right? Up here, we're at positive positions y, right? So it's our position y that tells us where we are along this axis. So this is going to be plus y squared. So now I can go over here and I can write for r squared. Well, r is the square root of r squared plus y squared, and I'm going to have that squared. So I just have r squared plus y squared here is what I'm putting in for little r squared. All right, so we've replaced little r squared with big R squared plus y squared, because this is the distance away as a function of y, right? The distance away for our little piece as a function of y. All right, we've replaced our dl, we've replaced our r, but we still have to deal with this sine phi, right? We have to deal with this trig function. And we've done similar things to this when we dealt with electric fields. Now, trig functions, remember, can be written as ratios of side lengths, right? And sine, specifically, sine, maybe we'll make a note over here, right? Sine of phi is always going to be the opposite of phi over the hypotenuse, right? That's what sine is. And so if this is our angle phi, all right, the opposite side here has length r, and the hypotenuse, well, we just figured out the hypotenuse is this length little r, that's the square root of r squared plus y squared, right? R over r squared plus y squared. So that's an expression then that tells us what sine theta is, so we can go and put that in over here. So this is r over the square root of r squared plus y squared. All right. Now we have an integral that's in terms of all the variables that we were given in the problem and this variable that we want to integrate, y. So that's really promising. So now we can actually go ahead and do this integral. So let's do that. All right. So big R is a constant that can come out front. Mu naught times I times big R over 4 pi. We're integrating from minus a to a dy on top, and on the bottom I have r squared plus y squared times the square root of r squared plus y squared. That's r squared plus y squared to the 3/2 power, right? Is multiplying those two things together. So now this is an integral that I can do, all right, or at least look up if you prefer, right? And so the integral of 1 over y squared plus a constant to the 3/2, if you go ahead and look that up, you get the following answer. You get that this is all the stuff in front, mu naught I r over 4 pi times, and then this integral ends up just being y over r squared times the square root of r squared plus y squared. And then we evaluate that at minus a and a, right? We need to now evaluate this at the two endpoints. So let's go ahead and do that. So we're going to plug in a for y here. All right, so this is now going to be all the constant stuff out in front again, over 4 pi, and then we're evaluating at the limits, so that's going to be a over r squared root r squared plus a squared, right? And then minus, and we plug in minus a, so minus a over r squared square root r squared plus minus a squared is just a squared, right? Minus a squared is the minus sign, minus 1 squared is just 1. All right, I've got a minus minus here, which is a plus. So these two things will just add together, right? They have a common denominator, so that will just add together. So now we're going to have mu naught times I times r over 4 pi times 2a over r squared square root r squared plus a squared. And looks like we have a factor of r that cancels from the top and from the bottom. The 2 and the 4 will reduce, right, just down to a factor of 2 on the bottom. And so we're left with a final answer that the magnetic field at spot P is mu naught times I times A divided by 2 pi r times the square root of r squared plus a squared into the page. All right, that is our magnetic field. And that was a lot of work, but we made it, all right? That's the magnetic field there. Now, there's one other thing that I want to point out to you before I end this video. And what I want to point out is I want to think about, it's good to always sort of assess your answer and make sure it makes sense, right? And I want to think about the case, well, what if I have a really, really, really long wire? Okay, what if A is much, much bigger than R? What's that going to look like? All right, so let's think about that a second. What if A is much, much bigger than R? Well, if A is much bigger than R, then this square root essentially just becomes A, right? This just becomes the square root of A squared plus some number that becomes negligible. And so this is just the square root of A squared, which is just A. So then our expression, if A, all right, if A is much, much bigger than R, this expression becomes mu naught IA over 2 pi R times the square root of essentially A squared. And the square root of A squared is just A, which is going to cancel with A. And we're left with mu naught times I over 2 pi R, and still into the page. And what I want to show you is that this is an expression then for a long straight wire, all right? What this essentially says is that if you have a long wire, the further away you get, all right, the magnetic field is going to get smaller and smaller linearly. If you run more and more current through that wire, you'll get stronger magnetic field. And the other thing that's interesting to note is if it's into the page on this side, right, What does it mean over on this side? Well, it means on this side it must be coming out of the page, right? That would just flip our cross product around, or you could also imagine, just rotating this around, right? It doesn't really matter how I'm viewing the wire, right? If the spot P was out here, I would just have the same picture and into the page would be this way, right? And so what you end up getting is that the magnetic field directionally, actually over here it's coming up, over here it's going to the right, up top it's going to the right, and then here it's going into the page, and then down there it'll be going to the left, right? So magnetic fields actually just go in circles around wires, all right? They loop around long, straight wires, and that's a really important result that will be really useful, that if you want to know the direction of a magnetic field around a wire, all right, that if you have some wire, maybe I'll let my red pen here be the wire. If this is a really long wire, what you can do is just think about the magnetic field as looping around the wire, all right? You can put your thumb along the wire and just loop your fingers around it, all right? And that will tell you the direction of the magnetic field going around that wire. And that is a very cool, useful result. So we've managed to use Biot-Savart to get some nice answers here. We'll do more Biot-Savart examples in future videos. So thank you very much.